Hello, and welcome to our second episode of Professional Presentation Series by Structural Engineering Institute, Graduate Student Chapter here at Michigan Technological University. We, the SEI, Graduate Student Chapter at MTU, are a newly established chapter, and we try to host outreach events in order to invoke interest towards civil engineering in the community and professional presentation to expand knowledge among peers in structural engineering. Professional presentations are also ways to promote state-of-art innovations and research with special focus on the needs of future generation of structural engineers. To keep updated on the events by SEI Graduate Student Chapter at MTU, please visit our website www.cee.mtu.edu/SEI. Today, we are thrilled to have a faculty from Michigan Technological University as our guest speaker, Dr. Stephen N. Morse, an assistant professor in the Department of Civil and Environmental Engineering and the Mechanical Engineering Mechanics. In addition to his teaching and research activities at MTU, Dr. Stephen Morse is the president of Standard Design Group, a software company that develops advanced window glass design. Today, Dr. Morse will be talking about architectural and structural use of glass. We will be providing time at the end of the presentation for any questions from the audience and for those who are joining us online. For our online audience, if you have any questions, feel free to submit your questions in the chat box and we'll address your questions time permitted. We'll also appreciate if the online audience will mute their microphones until the end of the presentation. Any questions not answered will be addressed via email in the following weeks, for which we'll be sending out a survey during the presentation consisting of 4 questions. We'd appreciate if you take out some time to fill in the survey. Without further ado, we'd like to welcome Dr. Stephen Morse.
All right. Thank you, Navajit, and thank you for inviting me here for the to present this presentation. So I'm looking forward to that. So we can get that hopefully out of the way. So to get started, I think I'm gonna get started. Let's see. There we go. We're going to do a quick overview about what we're going to talk about today. And I've geared this presentation with the assumption that most people don't know a lot about glass or how we design glass. So I'm going to go through some of the common design procedures that are used in the US currently, and then go through kind of what where we're moving on the committees as far as adding expanded ability to design new stuff, and talk a little bit about structural use of glass as well, because it's becoming very popular. For example, the Chanel store that was rebuilt a few years ago in Amsterdam is comprised of the entire kind of front facade is all clear glass blocks that they assembled and made a very striking, mostly transparent facade for that building. So really neat. All right. So let's talk a little bit about what glass is. So I'm going to talk specifically about soda lime glass, is what we typically use in architectural and structural use. First and foremost, it's a brittle material, which means that it deforms elastically up until a point, and then it fails. And often without any notice or any indication that it's fixing to fail. And it usually fails at relatively low stresses. So as far as a building material goes, this is not an ideal material to use for design for structures. So just a few properties. Young's modulus is around 10.4 million PSI. Poisson's ratio and density is there. So those are just kind of the material that we're going to be talking about. Over the past century or so, glass has been typically used to separate the outside from the inside. So in other words, windows in buildings. And before the 1950s, this product or glass was basically just specified by manufacturers that created the glass or made the glass. Between the 50s and 80s, there was a big push to try to come up with some sort of design procedure that designers and engineers could use to specify glass for buildings, kind of moving it away from just a product that was provided by a manufacturer. And then past the 80s, we moved into more of a probabilistic-based design in the U.S. Different other countries in the world use more of a stress-based methodology, but in the U.S. we went with a probabilistic method. And the question is, why did we do that? Before we get to that, I want to talk a little bit about what do we use glass, or how is glass used in buildings, and what are some of the common constructions that we see. So we can have a single glazed, or just a single piece of glass. This is more typical of what we saw years ago. We were just trying to close that opening for a window, and we weren't as concerned about the thermal conductivity of heat loss through our glazing. Well, that's become something that's very important to us because we want to try to make these buildings as energy efficient as possible. And so as we kind of advance, we switch to what are insulating glass units. And what that is defined as where we have multiple plies with airspace in between them. And because the temperature and thermal radiation has to transfer from different materials as it passes through that, it does a really good job providing insulation. And so most contemporary houses and structures are going to have some form of insulating glass units in them. Another type of glass type that we see used in buildings as well is laminated glass. And this is where we have two pieces of glass with a plastic inner layer in between them. And with that, it provides some safety performance to where, and oh, okay. Hold on while we address. Anyway, I'm going to keep going. And also provides some post-breakage performance advantages. Whereas if we break a piece of laminated glass, it generally stays all in one piece, and we don't have glass falling out of the building. So some nice attributes there. We can also heat treat glass, and with heat treatments, we start with basic annealed glass, and this is where when you throw the baseball through it, you have these big shards that fall out of the window. As we do heat treatment to it, we can get all the way up to what is tempered glass, and this is what we think about most commonly when your car, one of the car windows on the side of your car, in the door, if you will, breaks, and it breaks into little bitty pieces, okay? So that is because of that heat treatment. Something that's become much more popular in the past few years, especially for small personal electronic devices, is chemically strengthened glass. And this is where they take thin pieces of glass and through a process can strengthen the surface of the glass. We're going to talk about kind of how that works here in a second. And then something that has become more prominent over the past 10 years or so is what is vacuum IG units. And so this is a kind of an advancement over the insulating glass units where we had air in there. We're going to take this a step further, just like we use with our insulated mugs and so forth. We're going to take those two pieces of glass and then we're going to create a vacuum in that interior space. And we're also, and in order to make that work, we have to have little pillars that keep the glass separated, okay? So now, because we've removed the material between the two pieces of glass, it really limits the amount of heat transfer that can pass through the glass. And the advantage of these compared to insulating glass units are they are very thin, okay, for the same amount of thermal insulation, if you will. So for our discussion today, I'm going to define architectural use of glass as basically windows and our doors where we are separating the outside environment from the inside environment of the building, okay? Generally, they are designed to resist their own self-weight and environmental loads, so wind loads, snow loads, anything else that would impact a window or a door under normal use, okay? So some prominent examples that we've seen over the last few years, the Shard in London. Oh, okay. Now we're there. They don't have me. But they have this, hopefully they have that.
Yeah.
All right, now I'm back. Hi. The Shard in London, the farm in the Netherlands, this is a neat community building where they kind of reclad a community center all in glass, and they used some really nice, I believe it was ceramic frits, to kind of make portions of it opaque and portions of it see-through, but it's actually just all glass framed. Inside is shops and community spaces where people can hang out. It's kind of a neat space. And then some other ones that we've seen recently, the Spheres in Seattle, the Amazon Spheres. I recently had the opportunity to visit this, and it is a very striking building, both architecturally and just the glazing with it, because there's quite a few different pieces of glass, and most of them are rectangular, or excuse me, are triangular, but not all of them. So it's a neat looking building, and if you get a chance, you should go check it out. So for our purposes, we're going to say structural use of glass. What is different is that this is going to be glass components that are going to carry load from something else. They could carry load from adjacent members that they are supporting. For example, we have glass fins supporting a tall glass facade, and those are providing lateral support for those individual exterior windows. All sorts of different ways of using this, but the key thing is that in addition to its own self-weight and environmental loads, it's going to resist loads that are going to be transferred from other elements. So a new structure that's recently been opened up is this glass bridge in Guangdong, China, and there's all sorts of really neat pictures of this. If you haven't seen this, you should go check it out. But the entire glass floor all the way around, you can walk out over this large ravine, so a really neat space. Another one is the Sky Slide in Los Angeles, and basically you can go up to near the top of this structure, and you can slide down from one floor to the next. I'll bet on a blanket, but it's pretty amazing to be sliding down a glass floor. And as you can see, they're literally just hanging over the side of the building here. And we've seen a lot of prominent work done in many of the Apple stores, and this is one of the more striking spiral glass staircase. So kind of gives you an idea of what can we do with this material. You have the transparency, you can shape it in all sorts of different sizes and shapes, so you can come up with some really neat designs. And so what we want to do is figure out how do we do that safely. So let's talk about glass strength in general, and what is the reason why it fails at such a relatively low tensile stress. And the primary reason is that all over the surface of glass, we have these microscopic flaws in the surface, and those can be caused naturally as the glass solidifies. They also can be changed or modified or added through in-service conditions. That could just be from the environment interacting with the glass. It could be cleaning or touching or otherwise, all sorts of ways. But basically we have these little flaws, and what goes on with these flaws, we kind of model this as a side view. So we've kind of zoomed in and we're looking kind of through the thickness of the glass. Then we're going to have this little flaw here. And if we provide some tensile stress, what that's going to do is tend to sharpen the tip of that flaw. And if we create enough tensile stress and we get that flaw sharp enough, then we're going to have a large stress concentration, many times over what the original tensile stress was, to the point to where we create fracture, okay? So if we could eliminate these flaws, then we would have much stronger glass. And in fact, when we chemically strengthen glass, that is what they are attempting to do, is to use, among other things, certain salt mixtures to basically fill in some of these flaws where we're not allowing them to grow. They're still there, but we've kind of covered them up, if you will. All right, So how will we go about designing? So now we don't really know where these flaws are going to be. We don't know if they're going to be at the point of our maximum principal stress. This becomes more of an issue when we work with structural elements because we're going to have all sorts of different edges and stress orientations that would be different than the way we deal with windows or plates of glass. So one option would be, well, we can pick some limiting stress that we think is going to be okay, and we can just assume that the fracture is going to happen at where the maximum stress is located, okay? But what we find, especially with windows, is that, and especially for annealed glass, is that when we break glass under load, it doesn't always fail. In fact, it often does not, the fracture origin does not occur at the same spot our maximum principal stress was at. And so that kind of causes us some concern because we may actually be failing at a lower stress than what our maximum principal stress was. And furthermore, it was at a location other than the maximum principal stress. So that kind of makes it a little more difficult. We also find that not only does the magnitude of the stress, but also its orientation is affects because if our flaw is oriented such to where that tension is running kind of along the parallel to the flaw, then we're not changing that flaw tip. It has to be perpendicular and perpendicular. And anything that's off angle from that is going to lower that stress concentration. So where we get into that is can we use a probabilistic method? So in the States in the late 80s, a standard was advanced, ASTM E1300, to address how do we specify the thickness of glass to use in buildings, okay? And it was based on a probabilistic method, and it was pretty limited. And so I've listed the limitations of the current version, which is 2016, which is right now uniform lateral load. Well, that works great for windows in general, but not so much for structural elements because those have point loads. It can have all sorts of different loads on those that are not uniform lateral loads. In addition, it applies to monolithic and laminated glass, but only rectangular shapes. Now, we've all seen, in fact, I've just shown some examples of glass on building that was not rectangular. So how do we deal with that? And currently it addresses rectangular glass supported on 4, 3, 2, and 1 side. So we've tried to open that up, but it's still not, it's still pretty restrictive. It also does, back up. It also addresses insulating glass units for 4-sided support only, and it specifically does not apply to balustrades, glass floors, aquariums, structural glass members, and glass shelves. So clearly we can't use this to design our structural glass elements, okay? But we're going to start with this as a way into that. It also doesn't apply to wired glass, etched glass, and quite a few other types of glass that are used in structures. So up until 2016, the original procedure was that we used a series of charts. I'll show you one of those in a little bit. Based on the different standard thicknesses that plate glass comes in, and also with the number of supports that are that's were supported. And basically we'd go in there and we'd get a non-factored load from that, and then we would go through a series of steps to modify that non-factored load for glass type. So if it was heat strengthened or fully tempered, if it had a longer load duration, so if we were going to have this, something that was going to be under load for longer than, say, a wind load typically is. Also, we had an IGU configuration, so we had different thicknesses of glass in our IGU, and also the load sharing for those different thicknesses. So all of those pieces were in there for factoring. And so this is an example of what one of those charts looks like. And so quite a lot here, so I'm going to unpack this a little bit. So what we would do is we have, one, the thickness of the glass that this chart applies to. So in this case, 1/4 inch glass. And this is for a 3-second load duration. So this is something that we would use more for a wind load directly. And we have a short dimension and a long dimension, okay? And so the one question that we've run into is, what do we do when we have a piece of glass that's bigger than what fits on this chart? This is a problem. And then we have these radial lines. These represent aspect ratios. And so what we can see is that aspect ratio, or how square or rectangular our piece of glass is, impacts the strength of the glass. Also, we see that the area impacts the strength of glass. That's why we see as we go larger areas, the load, which is what these lines represent, becomes smaller. And if we have very small pieces of glass, those load lines get much larger. So if I want to design a piece of glass, in this case, say maybe a 90-inch by 60-inch piece of glass, then I just kind of figure out where those intersect, and we would find that we're sitting at about 1.5 kPa, and which is about 31.5 PSF, pounds per square foot. So with that, then we would go on to modifying our, for other factors. I'm going to come to that. One of the things that I get asked a lot is, what is the allowable stress of window glass? Okay, everybody likes designing with allowable stress, or at least some sort of ultimate stress for glass. And what I included this picture here to kind of illustrate that if I were just to translate this drawing, which has loads in it, and I were to give you the underlying stresses that correspond to these loads for these dimensions, we would get this drawing, okay, this graph. And what we find is that there's quite a bit difference in the single largest maximum principal stress depending on area and aspect ratio. So out here, we're saying that, well, that glass would have only had about a 2800 PSI stress in it. Whereas if I go to other areas, say something very small or something very square, then that number gets quite a bit larger. Okay, and this has to do with the way the stresses are distributed across the plate when it's loaded. It has to do with the aspect ratio in the area with respect to its thickness. So there is not a single stress that we're designing glass with, and this is kind of an artifact of that probabilistic method that we've been talking about. I'm going to go into a little more detail on that shortly. All right, so a little sidecar there. After we have our non-factored load, then we would use factors to address for heat treatments. Also for load duration. We have separate charts for laminated glass because the inner layer, the present of that inner layer, changes the way the stresses pass through the interior of the glass or through the thickness of the glass. And then we have a relatively simple model to deal with load sharing between our two pieces of glass of R3, depending on if it's a double or triple insulating glass unit. And so each of these things has its own limitations, but we've been using this method for about the past 30 years, and glass isn't falling out of buildings due to wind load. And so we feel like this method has been working just fine, but recognize that all those limitations we had at the very beginning, people want to do larger pieces of glass, different geometries, different constructions. We have new products that are coming available, like different inner layers materials that have other positive attributes that we like to take advantage of that just aren't addressed in the basic method of the standard. So to address that limitation, the committee that oversees the standard over the past few years worked to create what is an analytical procedure. And basically, we kind of gave the user the methodology that was used to create those original non-factored load charts so they could use it directly with their own in-house stress analysis software, say like finite elements, if you will. And they would have basically the methodology to either they could recreate a chart if they wanted to, but most importantly is use that method directly for whatever kind of configuration they have. So for a couple of reasons I'll mention a little bit is it was limited to 4-side support glass. And it does directly let you use the glass failure prediction model, which I'm going to show you a shortened version of really quick, or in a second. And then we also allowed, instead of just using a simple factor of 2 and 4 for different heat treatment types, you can measure the residual compressive surface stress of heat-treated glass, and you can use that directly. The way the standard is written is that heat-treated glass has minimums for residual compressive surface stress for those to be considered either heat strengthened or fully tempered. And the standard requires you to use the minimums for design because you don't know what you're going to get when somebody goes out. You've created a glass design, and then the contractor is going to go and find somebody to actually make the glass, and you don't have a way of knowing whether you're going to get what are residual compressive surface stress you're going to get. So we just use the minimums. But forensically, one could go back and check that if they wanted to. The standard for the charts for laminated glass were based on symmetric laminated glass, which means that both plies were the same thickness. There's various reasons why somebody might want to make those different. And so we provide the keys, if you will, the methodology to take advantage of that. Also, it incorporates the ability to use interlayers other than PVB. Most notably, that's pretty popular in the industry right now, is ionomer-based interlayers, which tend to be quite a bit stiffer. But there are also stiffer PVB interlayers that are on the market as well. But this one just, currently the charts just have the regular one, all right? And for insulating glass units, we have those 2 pieces of glass and we have that sealed airspace. That's what makes the system work. And because we have that sealed airspace, we now have a really funny shaped pressure vessel. And the idea here is that when we apply a load to one ply, it compresses usually the airspace in between, thus increasing the pressure interior, and then that is transferred to the second piece of glass. And there's some equilibrium that occurs there, and it follows the ideal gas law, because just as we reduce the volume, pressure goes up. The other light is going to deform a little bit, so then we're lowering the volume, or we're increasing the volume again, so pressure comes back down. You get the idea, okay? So we need to take that into account to get accurate load sharing estimates between the 2 pieces of glass. Something that I haven't touched on, but the original standard was predicated on a probability of breakage of 8 in 1,000, which sounds like a really weird number, and but that's the number that's in there. And the idea would be that we had to perform our glass failure prediction model calculations and figure out what was, for a given geometry, so rectangular dimensions and thickness, what was the load that would give us a probability of breakage of 8 in 1,000? So that's kind of an iterative procedure to guess. And what I've shown here is just, if one were to try to find that, we could just pick some loads and we just keep increasing it until we go from something close to 0 in the probability up to something near 1. And then we could go find where that is. So if we zoom in, we can see that, all right, well, our probability of breakage for 8 in 1,000 would correspond to a non-factored load in this case of 148. Okay, so this is the way those charts were created that are in the standard. But for our purposes, when we're going to use the analytical procedure, we don't really necessarily care about what the full load resistance of the unit is. We just want to make sure that whatever we have for the load that we applied to it has a probability of breakage that's less than or equal to 8 in 1,000. If we have that, we're done. Now, if we were curious on what the capacity would have been, then we could go through this process and walk it up and figure out what is the magic load. That is, and depending on the construction, that may be 5 PSF away, that may be 10, 15, 20, depends on what it is. So it can be something close, or it can be something quite a bit higher depending on where we're at. So this is that glass failure prediction model that I was mentioning. I'm not going to go into a whole lot of detail with it because nobody wants to look at a bunch of equations. But the key things here is that we see in this that we have duration, that's TD, so we can take into account that. We have RCSS here. We also calculate the representative areas and stresses associated with those. So this is where our finite elements packages are going to come into play. And then we just have to sum this up in the calculation. So without a whole lot of effort, one could translate these equations into a quick little Excel spreadsheet calculation. And all you have to do is do your analysis in FEA, copy those stresses and areas out of that program, paste them into your Excel spreadsheet. Voila, you can calculate the probability of breakage. So that's not too bad, even though these equations look kind of nasty. This C here is a polynomial that was created to represent the biaxial stress correction factor. That's what this actually does. And this has to do with adjusting our probability for whether or not our stress is at a particular angle with respect to the flaw, okay? So it's kind of taking that into account. And it's based on the ratio of the minimum maximum principal stresses. So again, this is the same procedure that was used to generate the charts that are in the standard. So how would this work? So for a piece of monolithic glass, so this is a solid piece of glass, we're going to perform our stress analysis. We're going to plug that into our whiz-bang spreadsheet that we just made. And we're going to check and see if we're less than or equal to 8 in 1,000. If we are, we're good, we can move on. If we're not, then we need to make a change to our design, either make it thicker glass, heat treat the glass, do something to get that number to come up. So we have some options there. I'll show you some examples here in a little bit. For laminated glass, in this case we have two methodologies that the standard allows you to use. One is the effective thickness model. Because layered plate analysis is somewhat complicated and we need to be able to model that inner layer appropriately, you have to have a fairly sophisticated package, FEA package, in order to do that accurately. And it also tends to take a while as far as doing the calculation. So what the standard allows you to use is come up with using a fairly simplistic method, come up with an equivalent monolithic thickness that would be representative of the laminated glass. And then we can then use FEA with monolithic glass with the kind of these effective thicknesses to do our stress analysis and to check for deformation. So I have over on the side here a asymmetric laminated piece of glass, and with that we would expect our two effective thicknesses to be different, and then we would perform that stress analysis. We plug that into our whiz-bang spreadsheet to do the glass failure prediction model, and then we're going to use the principle of weakest link here as whichever one gets to 8 in 1,000 first, that's going to be the one that limits our design. And so we're just going to take the largest of these two probability of breakages, and we're going to make sure that that is less than or equal to 8 in 1,000. If either one of them happens to be larger than this, then we have to make a change in our construction because one of the plies doesn't meet the requirements. We're going to see a similar procedure when we use insulating glass. And with insulating glass, we now have two different pieces of glass that we have to analyze. And we also have to deal with the load sharing between those. So very simplistically, if both pieces of glass were the same thickness, then they would share the load somewhat evenly. It's not exactly, but we can say it's close to 50% each. As those are different shapes or as different thicknesses, that moves around. And then we perform our numerical analysis, and then again, same principle, weakest link is where we have the checking for the largest of the two pieces of glass and make sure we're at less than 8 in 1,000. So that's not too bad. We could see that if we could branch out, if one of these was laminated, then you would see that, you know, break out, and we would have to do 3 stress analyses to make that happen, okay? Potentially if we're using the effective thickness model. The other alternative is to model the laminated glass directly as a layered system, and then you don't have to worry about doing the effective thickness model. So what would the procedure look like? Let's say that I wanted to design a piece of glass that was 76 by 38 and inches with 1/4 inch, and I want to see, can it resist a 40 PSF load, okay? So we would key that into our FEA program of choice, and we would get a whole lot of stresses, presumably in some sort of grid, depends on how you do it. And so all I've done is just tabled those values here, okay? So don't expect you to remember all these things, but the idea is that we have those, and then we have the minimums. We have tributary area that comes out of that. So in this case, I use kind of a uniform grid in my example. And then we're going to plug that into our spreadsheet, and we're going to use those ratios, the maximum, minimum, principal stress at each point to come up with our biaxial stress correction factor. That was the C, right? And then we bring all that together into our summation, which was B, and then we can calculate finally our glass failure prediction model, or probably a breakage, excuse me. And so in this case, we came up with 6.48 times 10 to the minus 3, which is less than our 8 in 1,000. So this design works. It's close to being maxed out. So its load resistance is probably a little bit higher than 40, but it's not much higher than 40. So if I wanted to repeat this process with laminated glass, some things that we need to know is what is our laminated construction. So here I'm using asymmetric construction because I can. The rectangular dimensions are the same, and we have the thickness of our inner layer, and we have a material, so in this case PVB, and I used for the shear modulus for PVB as about 62 PSI, okay? Oop, I went too far. Last thing is that I'm gonna check this for 50 PSF, not an uncommon design wind load for Windows. And we perform those effective thickness models, and we've calculated probability of breakage, and we see that one of the lights worked and one of them didn't. Interestingly, was that the, in this case, the thinner one did not work. Is that right? Yeah. But that's depending on how it works and what heat treatment you have, that can flip around. So since that doesn't work, this design doesn't meet our requirements. And so what can we do? What can we change to fix that? Well, I could increase the thickness. So I can make it a little thicker. And we see that now that works. So just increasing one of the ply thicknesses fixed our problem. Alternatively, we could have used a stiffer inner layer. So instead of using the PVB inner layer, I could have used something more consistent with an ionomer inner layer. And we see that that G value goes way up, and now it works. So I didn't have to change the glass thickness. I just changed the inner layer I chose to use. Also, I could have chosen to heat treat that ply. And we see that when we do that, that one goes way down, okay? So we have several different options there on how we can change the configuration and make the system work. Previously, because it was just based on pre-calculated charts, we didn't have these options. Either we could heat treat all of it, but we didn't have a way to check for different interlayer properties or for different thicknesses of glass. We didn't have that option. We just had to choose a thicker construction. Real quick, if I want to do insulating glass, similar process. And in this case, we chose a 530 seconds with a 1/2 inch airspace, and calculated our load share between the two of them. Notice that those were close to 50%. But they were a little bit off. In other words, the loaded light's going to carry a little bit more because there's a little bit of squishiness in our airspace. We don't transfer all that because we have a compressible gas in there. And so in this case, that design worked. So I'm going to give you a couple of comparisons. One of the questions is, well, you've got these two different methods. How do I know which one to use? Okay. So I want to show you a couple of comparisons on, I'm going to go through these kind of quickly, just to see how much difference does it change when we use what we had previously, the basic method, versus what is the new analytical procedure. So for monolithic annealed glass, there is no change because this is exactly what the charts that were in the standard were, and so there's not a difference there. So this is the same chart that we had before. Now, if I want to go to heat strengthened glass, then the process there would have been we took the non-factored load chart and we multiplied by 2. So we'll see that all these numbers increased by a factor of 2, and I just redrew the chart, or really I just adjusted the numbers. And then if we were to use the analytical procedure using the glass failure prediction model, where we now took the RCSS to be 3,500, which is the minimum required for heat strengthened glass, then we see that we have a load contours that look like this. And so those moved up quite a bit. So we have, this was a 1.25. You can see it in green a little, barely down there. And then below is, and now it's up to a 1.5. So we get a sense that it increased, but it's not real clear how much or where it increased. So we can divide those two charts and we can come up with these contours, which is the analytical procedure value divided by the basic procedure value. And we find that we had up to a 1.8 times increase when we're out here at these aspect ratios near 3. And we see that that changes depending on where we're at. And we get down to 1 and even a little bit less than 1, but not much, at these very small sizes. Otherwise, just taking advantage of the RCSS and the glass failure prediction model gives us a pretty good boost on the strength of our glass. Now, it's not to say that the glass automatically got stronger because we changed the design procedure. The way I like to think about this is that we knew the glass was stronger than what we were designing it for through experience. And what this method allows us to do is to design our glass where its capacity is closer to reality than it was before. Okay, whenever we design anything, we don't want to be in a situation to where there's this big kind of fuzzy area. We know it's stronger, but we're not real sure how much stronger it is. But we're pretty sure it's okay. And you can see how that can lead to making bad decisions potentially when you start kind of leaning into that fuzzy area. So this is going to tighten that up for us a bit. I will tell you that even with this increase, the glass is actually still stronger than it is, or than this estimates it. But we've definitely kind of narrowed that gap a little bit, and we have it now in a way to where it's actually a function of RCSS, because we're going to find when we do fully tempered glass, the minimum RCSS there is 10,000 PSI. Now, when they make heat-treated glass, the people that run those machines do a great job. It's truly an art form to get those to work properly. And they, for heat-strengthened glass, these things are, you can't dial them in super precise, so they're going to be a little bit above what that minimum is because they want to make sure that they don't have a piece that comes out that slides below the minimum, right? Because that's what we're doing. So we know just by the way stuff is manufactured that the glass is going to be a little stronger because it's going to be manufactured at a higher RCSS. Well, the previous standard, or the previous, the basic method didn't address that at all. It just said, doesn't matter what it is, it's 2. And then magically, when we get to 10,000, now it's 4, okay? So one would say, well, there should have been at least some gradient between those two. In reality, there is. Well, our standard has the capacity, or the analytical method has the capacity to analyze glass with respect to that. But again, we've kind of chopped it off to the minimums for design usage. So we're seeing similar contours, in this case, up to a 2.2 times difference between the two of them. And so that means that, according to this analysis, that this piece of glass is 8, almost 9 times stronger than just regular annealed glass, okay? And that's at the minimum, okay? It'll go higher if the RCSS is a little bit higher as well. Again, same principle. They don't leave it at the minimum. They usually go a little bit higher than the minimum to guarantee they don't have one slip through that drops below that. So I'm going to go through these a little bit quicker. If we compared the laminated glass to the charts, we see that the effective thickness model overestimates the strength of our laminated glass for aspect ratios around 1, so up in this upper region of my chart. So that's not ideal. There's some issues there. We can play around with different constructions. We see in some constructions, asymmetric, it actually shows that it's weaker in some cases, parity in others. And if we go to insulating glass units, we see that those are relatively close for symmetric. All right, because we saw when we did our example that the load share was close to 50%. It wasn't that far off, so we don't expect these to move around much. But what happens when we start changing the thickness of our glass in our IG unit? Does that hold true? And we see that we start seeing upwards of 10% difference depending on where we are. In some cases, it's the same. And we also find, I'm just going to toggle back through these, this is the same construction. I just reversed what side the load was on. And we see that the pattern and the magnitudes of those change a little bit, and indicating that the orientation of our IG unit construction to the load makes a difference on its performance. That was not available to us in the analytical method, or in the basic method. We mentioned triples, so this is an example of a triple IG again. Not a huge difference there, less than 10%. But if I start doing asymmetric triples, then we see that there's quite a bit difference. Also notice if I have loaded the thinner one, where it's saying that that's going to be about 20% weaker in some areas, others 25%. If I just flip that around, now it's 25% stronger, okay? Now, when we think about wind loads, you know, we have negative and positive pressures available to us. And so now we're looking at, okay, what is the orientation of the load and compared to the orientation of the construction of the IG unit. And one thing that we see commonly, especially with double IGs, is we would typically see this construction where you have the larger light on the exterior to offset the pillowing effect. And so if you've ever been to a downtown area where it's really cold, usually it's very noticeable. You can see some weird undulations or reflections on the glass. And what that is because that airspace either expanded or contracted. And the further are you away from the building, the more noticeable that deformation is. And so what to combat that is if we put the thicker one on the outside, then that will stay relatively flat. And the interior one, which we don't care too much about, will kind of allow that airspace to expand and contract, and you don't see that deformation. So this is kind of a contemporary way of doing it. Now in your residential usage of glass, your windows in your house, those are usually symmetric, okay? But we're seeing high-end high-rises going in, that's typically something like this, not always. The northern climes, we're going to see more of the triples because to get the insulating factors to go up. All right, in this one, I've actually a little bit different analysis. Is I wanted to compare if I use the effective thickness method versus the using a full layered FEA model to see how well did the effective thickness model work compared to doing a full FEA model. And we see that depending on where we're at, there can be upwards of 10 to 15%, at least in this construction. Different constructions, it can be more so for that process. All right. So for a summary, the analytical method, heat-treated glass is modeled stronger. We'll say that it's modeled closer to what its actual strength is. Still conservative. Laminated glass, we can do different construction types, so on and so forth. And for insulating glass, dealing with our sealed airspace directly using the ideal gas law, we're going to get better load sharing estimations between our pieces of glass. So those are important. I want to give you a quick update on what's coming up on changes in the standard. So this is stuff that's in the pipeline. I mentioned before that the charts in the standard were limited. People wanted to use larger pieces of glass. And part of that is a response to float lines have gotten a little bigger. People are able to transport larger pieces of glass around to the job site, so on and so forth. And so what I have here is showing the 12 mil PVB laminated four-side support chart over here on the left. And on the right is the proposed new version. And so we went from 5,000, so that's 5 meters for us in the US, 200 inches. We've doubled that, so we can do up to 400 inches. And so that's a really long piece of glass. I think currently people don't manufacture ones quite that long, or even up in this area here, due to limitations of the way you can make glass. But it's better to have the chart a little bigger than to have to come back another couple of years when people do start making glass that big, potentially, and we don't have to do the charts again, because this is just an analytical operation to do the calculation. So we can go as big as we want for the most part. So this is 4-side simply supported. This is our 3-side simply supported chart. So notice that we have a little bit different shape. Aspect ratios, the extent of the chart change a little bit between the supported and this is the unsupported versus the supported edge. And in that one we added more lines. So there's more, you can get, depending on if you're outside up here or down here, you can still design those. For 2-sided, we had a series of straight line charts were based on pretty much just beam action alone. The reality is if you have a plate supported on 2 ends and you have a uniform load, it is going to principally appear to behave like a beam, but you're also going to see it kind of fold in a little bit. In other words, we can see those unsupported edges rolling up some, okay, because of the way that plate action, the membrane action of the plate is going to work. And so if we kind of use that with our glass failure prediction model, we actually see that there's a little bit of a bend to these, okay, when we do that. So now we're going to go from one chart that had all the thicknesses to each thickness potentially will have its own chart similar to 3-sided and 4-sided. Again, these are drafts. This has not been balloted yet, so that's there. 2 sides. So another thing that's been happening over the past 20 years or so is that one of the prominently used skylight standards in the United States specifies that skylight should be designed to probably a breakage of 1 in 1,000. Well, there's never been a 1 in 1,000 chart for designers to actually go and look up the capacity of glass. And so what's happened is that designers were left to kind of make up a factor, okay? And people have been doing that. Well, the committee decided, it would be nice if people could just use a chart that was calibrated to 1 in 1,000. So the committee is looking into the possibility of adding charts to 1 in 1,000. Okay, so you'll notice the dimensions here are a little bit less, and these capacities move down quite a bit. Now, if I were to go to the operation of dividing the 2 charts and ask, well, was there a common factor between 8 in 1,000 and 1 in 1,000? And the short answer is no, but there's a range of factors, okay? And so one could say, well, I'll just take whatever the worst deduction is and go with that, which you could do. But the idea is that if we use the method directly, then we can potentially come up with a more economical design. In other words, we're going to design it as the strength that we believe it is, and potentially have a little bit thinner glass on the building. Now, some might argue, well, it depends on the geometry and depends on what you're doing. It may not make a difference at all. And that's true. But if it does, we would like to take advantage of that, because think about it. Glass was heavy, right? 156 pounds per cubic foot is the density of this stuff. We're going to clad the entire exterior of the building in it. And so if I can make all the glass on the building a little bit thinner, then the entire structure got lighter, right? I don't need to have as big a columns and as big as beams to support all of that weight on the exterior of the building, and that kind of trickles down to the entire structure. And it's less glass, so the glass is cheaper, right? So there's some advantages economically to using what it is as accurately as we can. A few other updates that are coming. We've added material properties. Interestingly, the standard never really defined what glass was as far as it was concerned in the standard. So we've added that. We've added some notes on where to go find material properties for interlayers. We are in the process of adding the glass failure prediction model to free edges and partially supported edges. And this is the piece that will will open up the standard to use the analytical method for different, for any kind of geometry and also for any kind of edge support. Going to add some deflection requirements, and the committee is working hard on adding some advice on glass with ceramic frit. So that's being worked on. I want to touch a little bit about the committee's work on structural design of glass. So right now in the United States, there is not a design standard that an engineer or a designer can pick up and use to design glass elements. The way people have been doing this is they have been using their engineering judgment and what their understanding of the way glass fractures and works. They make a design, and then more often than not, they have to do full-scale tests to prove that their design works. Oftentimes, they have to prove that it works for significantly larger loads than they actually need, or they're actually designing for, because people want to be reassured that it's not going to break. And that's really expensive, okay? And so what we're trying to work towards is a consensus design standard that somebody could go in and design different glass elements. And so my colleague Richard Green has been leading the charge on that for the past several years. And he and his team have actually completed a working draft of the standard. And they are now in the process of going through and checking that to calibrate and verify that it works for common glass structural elements that are used, that people have been designing for a while, we feel comfortable with, and see, is it working, okay? One of the central issues that makes this process difficult is that there's not a lot of data out there for the strength of glass for different scenarios, for different shapes, for different construction types. And so we're left to kind of use some expert opinion on how to design glass or what factors to use. The problem is, as engineers, we're used to design standards being based on statistical analysis of material properties, and there's a huge body of data. And so the factors that are in the standards, we can trace back somewhere. What we have with glass is that because we don't have that much data, it becomes difficult to get the numbers we need to make the standard. So we're having to select some and then check and see if it works the way we want it to. So here at Michigan Tech, I am in the process of doing several different types of research, looking at point-supported design procedure, looking at insulating glass units, load sharing when we have partially supported edges, and There's various reasons or various cases. Some people specifically design IG units that are two-side support and trying to account for the stiffness that the spacer provides and other things. That's why it's partially supported. Looking at cold rolled and hot rolled curved glass and how do we create or calculate load resistance for that. Load resistance of glass with ceramic frits, and also working on trying to get into what is the load resistance of vacuum IGs, because we have this amazing product that does a great job of insulation and it's pretty thin. And so it'd be, if nothing else, it'd be great to go retro some buildings here on campus with that because there's a lot of single glazed windows on campus. But right now, people really don't know how to design it. They don't know what constructions work, what their failure modes are. And so I'm working to create a standard so people can use that, and then hopefully we'll start seeing that product more widely used in the States. On the structural side, we're working on trying to quantify what is the strength of edges for different treatments and different glass types. And so this is actually our preliminary rig. We're in the process of making a much larger one and doing bigger samples. So that's going to be fun. I want to share with you just a quick, we also have a destructive, let's skip some of that, a destructive pressure frame to where we can load a piece of glass to failure. This is a previous one that I've used. And, but we're in the process of building another one that's going to be a little more modular and accommodate a bunch of different sizes. So we're looking forward to that coming online this summer. And hopefully we're going to get to test some vacuum IGs in this rig. So pretty cool. Let's skip that. I'm also with some colleagues working to create a glass and facade course that we offer here at Michigan Tech. And that's probably going to be offered online as well as in class. So that's going to be something that I'm hoping in the next couple of years I'm going to be able to roll out. And that's going to do more than glass. It'll talk about extruded aluminum. It'll talk about the design loads that we typically have to deal with, facades, environmental loads, capacities, and pretty much whatever we can squeeze in there. So it's going to be a fun class. Because currently, right now, glass and facades is not typically taught in engineering schools. And so I want to help change that. Anyway, I appreciate your time and certainly happy to entertain any questions regarding that. I know we ran a little bit over time, but I'm happy to hang out if we have some questions.
Thank you, Dr. Morse, for your interesting and informative presentation on glass design. Now we'll have our Q&A section. So if there is a chat going on, I'll see. We'll read out the questions and we'll go from there. And if not, we'll also open up the mute stuff over here so that if you have questions, you can unmute yourself and ask questions. Over here.
We have one question in chat box.
Yeah, I'm looking for it. So the question is from Matthew Bolchik, and it is what kind of new applications, public usage, do you think would be enabled if window strength was significantly increased?
It's a good question. I haven't really thought about it from that point of view. I guess if window glass was stronger, you would potentially be able to use larger pieces of glass or fill larger openings with a single piece of glass. So kind of getting away from having intermediate mullions or framing for those. Now with that, you're still going to have issues with deflection. So even if we ramped up the strength quite a bit, you still have to address the deflection issue. There is a few researchers in Austria, Jürgen Nagebauer is one of them, that is doing research with large chemically strengthened panels. And he's looking at the feasibility of making more flexible structures out of glass. So think about a canopy that instead of being made out of cloth or some other flexible material, you could stretch one out and have a glass canopy that could fold or change shape or move around. So he's done some exciting work in that area. And he's also principally been looking at how do you quantify the strength of chemically strengthened glass, because the traditional 4-point bending method that's commonly used in Europe doesn't work with really, really thin pieces of glass because it's too flexible. And so he's been doing a lot of work on coming up with a test procedure to figure out that strength. So hopefully that answers your question. If not, I'd be happy to follow up with you later. Anybody in the audience have a question? Yeah. Yeah.
I think your research is very interesting. I have a question about because the glass structure a little bit different with other kind of solid structure. Because you tell us the fractures usually at the relative low tensile stresses. I'm wondering, do you have some construction model to calculate where it will break in the glass structure?
Okay, so it's a great question. So if we were to just look at it from a general material point of view, we'd be looking for where is the point that has the maximum principal stress. So we could take whatever shape we have, we could do an FEA analysis, and we could figure out, okay, this is where we think the largest stress is going to be. What works against us is that we know the surface has these flaws randomly located all over it, okay? And because we know those flaws are the mechanism that reduces our strength, it becomes very difficult to sync those things up. Now, if the glass is heat treated, then we do see that analogy of, or that, you know, the idea that the maximum stress is going to coincide with the area that it breaks. As we increase our heat treatment, that becomes closer to being true. But a lot of our structural use of glass is actually based on annealed glass because it stays very, very straight. And there's some other issues with it that are beneficial. And so we're back to having, well, we're not really sure where that critical flaw is going to be. And so that's where the probabilistic method comes in, is that we don't know really where the point of failure is going to be, but we can have a probability that a failure may or may not likely occur. So I feel like I kind of walked around your question a little bit. The short answer is no, I don't know where glass is going to fail when it breaks, especially with annealed glass.
You can use the curves to predict where.
Well, not so much where, but when and what magnitude of load. But it doesn't necessarily tell me where that fracture is going to happen. So when we've done like that full scale where we loaded the piece of glass until it exploded, we've done a large number of those. And for annealed glass, the fracture origins are all over the place. There's not really a consistent pattern of them. You wind up drawing a very large circle around, you know, if you fold it over for symmetry, so have a pretty large circle where it fails versus where the maximum principal stress was each time. Yeah. Yeah.
I just have a question because I investigated the concrete.
Yep.
Sometimes the concrete has a durability problem. I want to know if the like the mechanics property of the glass would it change with the time or the
Yeah, excellent question. So the standard is calculated, or it's calibrated is the right term, for approximately a 20 to 30 year service life. And so what we see with annealed glass is that when it's brand new, it has a certain strength, and over the course of 20 to 30 years, we see that strength reduce about 40%. So the standard is calibrated to have the glass at strength, 20 years down the road, and it kind of levels out, okay, to where we don't see a continual decrease, because the mechanism is that through its in-service life, those flaws are changing. And we're getting more of them. And so that's where that strength goes down. But we get to a point to where the flaws, sometimes we have so-called flaw healing, so that, due to water, moisture, other things, they can round them out. Then we have new ones being created, and you kind of hit this steady state, and that's about that 40% mark. So great question. All right.
One more question from the online audience.
Okay.
All right. The question is, are present standards relevant to quantify windows' risk of fracture during earthquakes or during high-speed projectile resistance in hurricanes or tornadoes?
Great question. I think the short answer to that question is no. So when we talk about earthquakes, we have different failure modes that can occur. You have racking, and what happens with racking in a standard window point of view is that you can potentially get the plate or the edge of the glass to impact the frame that's holding it in, and then you can cause a failure that way. Now, that you can estimate, and you can leave enough space around it for your displacement that you're expecting to have to attempt that that doesn't happen. But that's not really a glass design issue. That's a structural frame issue, right? And so, but the standard doesn't really give us, there are some industry standards on what is used, but our strength standard does not address that. Now, we can have other failure modes with earthquakes, and I'm thinking in terms of windows. I will say that in our proposed structural use standard that we're working on, there is some factors that deal with that. Part of that is because it backs into the standard ASE 7 loads also, which incorporate earthquakes. And Richard would be the best person to check with that, and I left his number on the presentation. He can speak a little bit better for that. For hurricanes and tornadoes, we're talking about debris impact. Pretty much debris impact for any material is extremely difficult to design for, because there is so many different things going on with that, and it's a very energetic and dynamic problem. And this is why we have our so-called 2x4 cannon shot, to where we're going to simulate debris impacting our structure by shooting a 2x4 through the air and impacting. And that could be doors, that could be glazing, that could be walls, it could be anything that's on the exterior of a building. And we see that being required, especially in hurricane zone regions like Miami-Dade is one of the big ones. There's all along the Gulf Coast and the East Coast. There are similar requirements, probably not as extensive as Miami-Dade is, but it's still there. So hopefully that answers your question. If not, shoot me an email. I'll be happy to follow up with you. Anybody else have a question?
May I do last question?
Oh, okay.
Yeah.
Last question.
Yeah. So you say that people are moving for a bigger construction of glass.
Yep.
But if we think about it, more the area, the more is the probability of breakage, because the flaws are more.
Right.
So I still don't understand why we are going for bigger construction, because we can have, say, if 20 feet by 8 feet maybe a glass, we can have a 10 feet by 8 feet and 10 feet by 8 feet with a connection on the middle. So why 20 feet by 8 feet?
Well, I would say it's principally due to architects, and they seem to dislike having things that break up the view. Okay, and so if they had a choice of not having an intermediate element for strength and having one, they would go with not having one, because you just have, because think about it, if you're in a giant window, you don't want to have anything that interferes with your view of the outside. You paid a lot of money to see the outside for such a big window. You want to see all of it. That's the rationale. And And that's the kind of fun part of my job, is to try to figure out solutions to what people want. So that's kind of what engineers do in general, right? So, well, thank you again, and I appreciate everybody's attendance.
And we'd like to thank Dr. Morse and audience. We'll be sending out a short survey tomorrow. We'd appreciate your feedback in that. Also, if you have any more questions, you're free to email Dr. Morse, or feel free to send us an email at SEI@MTU.edu. Even also, if you have an interesting topic to present and would like to use our forum as a way, yeah, please feel free to contact us as well. Thank you so much, and you all have a good evening.